Hello everyone, and welcome to Recitation with Sohail. Today we're going to do problem 37 from section 3 of chapter 6 of the 10th edition of Boyce and Diprima. So for this problem, we want to calculate the Laplace transform of a periodic function. Namely, it's the function f defined on the right half of the positive real line, where we first define it on 0 to 1 by just letting it be t, f of t equals t, and then we extend it to be periodic with period 1. Here is a picture from the 10th edition of Boyce and Diprima of the graph of this function. So as you can see, between x is 0 and x is 1, the function is just f of t equals t, and then we just start repeating it to make it have a period of 1. So this is our function f of t, and we want to calculate its Laplace transform. So to do that, our first goal is to rewrite our function f of t in a more convenient form. We want to have an algebraic formula for f that we can manipulate instead of just a picture and a description with an English sentence. And in order to get that algebraic formula for f, that algebraic expression for f, we're going to have to use the step functions. And I'm going to use the notation used in Boyce and Diprima. In other textbooks, you might see different notation. But our step function is going to be uc of t. So uc of t is the function that is 0 when you plug in any number smaller than c. And then if you plug in any number bigger than or equal to c, it becomes 1. So it takes a step up. Here is a picture of the step function uc of t, also coming from the 10th edition of Boyce and Diprima. As you can see, right before c, or always before c, the function is 0. We have a dot at c to signify it's 1 right there, and everything after c, the function value is still 1. So this uc of t is what's going to help us get the algebraic expression for the function f. Now, I'm going to use uc of t and make a new function. So I'm going to take two of them. I'm going to take uj of t and uj plus 1 of t, and I'm going to subtract them. And that's going to make a new function. So I'm subtracting two different step functions. And what's going to happen is this difference of step functions, it'll be 0 for anything smaller than j. It'll be 1 in between j and j plus 1. And then it'll be 0 after j plus 1. So to see that, we see that this uj, we can correspond this to what we already have, the uc of t, right? So we can just call, so that's kind of like our uj is uc. And then our uj plus 1 is going to be the following. Right, so that's going to be my, I'll just write c plus 1 since we already have c in this picture. So the uj plus 1 would look like this picture here that we have in the c plus 1. And then we see that, sure enough, oh, sorry, let me actually add a tiny bit more. So here is the, there we go. That's the c plus 1. So now we see that between 0 and c, or really just anything before c, both of the functions are 0, so when we subtract them, it's still 0. Between c and c plus 1, where c is included but c plus 1 is excluded, uc is going to be equal to 1, but uc plus 1 is going to be equal to 0. So when I subtract them, I get 1 minus 0, which is 1. And that's why we have this second part here, this 1 right there. Right? And then after that, at c plus 1 and beyond, both of the functions are equal to 1. So when we subtract them, we get 0. And that's where this formula comes from. So this section corresponds to this, and then this section corresponds to that, and that section corresponds to, oops, sorry. So fiddle around with this highlighter. I guess, yeah. Or I could have just done that, undo it. Yeah, that is one of the difficulties of these. There we go. So that's where the 3 sections correspond to. You don't need a picture. You could derive this formula directly from the definition of the step functions, but I think the picture helps make it more clear. So now this difference of step functions is really going to help us out, because basically the point of all of these calculations is that this difference of step functions lets us isolate the region between c and c plus 1, or j and j plus 1. So we have a little bump, a value of 1 between c and c plus 1, and then we're just 0 everywhere else, and nothing happens in all those other regions. So using this, we can get the following formula for f of t. We get that f of t is equal to the sum, j going from 0 to infinity, of this step, right? Uj(t) minus uj plus 1t is the step in between j and j plus 1. And on that step, we have the value t minus j. And then off of that step, t minus j is irrelevant. And then we add this up for every j. So let's examine this equation 3 in some more detail, because this is a pretty important part of the problem. If we go back here, we see that so this is just the function f of t equals t, right? Instead of f of t equals t from 0 to 1, I'm just extending it to go from 0 to 2. And then we see that here, the actual value of f of t after 1, it's not t, it resets. It's because we just copied the first part of the graph over. So we see that from here to here, we have a step size of 1, right? The function value up there is 1, but now I have to subtract 1 to reset that to 0. And then I'm going to keep increasing like t, like the way we did before. So we start off between 0 and 1. It's just t, which is like t minus, which is t minus 0, right? So this section between 0 and 1 is the u0 minus u1. It isolates this little section. And then on that section, I multiply it by t minus 0, which is just t. Then after that section, it's the section from 1 to 2. So this section is u1 minus u2. And on this section, I don't multiply by t, because that would be the purple part up here. I have to take my t and subtract 1, this drop indicated by the brown, to get t minus 1. So between 1 and 2, the function value is t minus 1. And that's why I have t minus 1 times u1 minus u2 in order to really restrict the u minus 1 to that little section and not have it affect any other section. And then, sure enough, you could imagine that if I was to continue this a little bit, oops, let me reset that over here. Right, so if I continue this graph of f of t equals t, then I can see that once again, here, that between 2 and 3, just the ordinary function t is way up here. And to drop it from here, right, so here t is 2, so the function t has value 2. I drop that down to 0, so I'm subtracting 2. And then I'm increasing like I normally would. So this part is t minus 2 times u of 2 minus u of 3 to restrict it to that section. And then the pattern continues, right? T is going to keep increasing way up here, and I'm going to have to keep dropping it by more and more to reset it to 0, and then multiply it by the difference of step functions to get this little, the next little chunk. And since there's an infinite number of chunks, I have to keep doing this indefinitely, infinitely often. So that is where we get this formula, the formula in 3 for f. And then now that we have the formula, the next thing we note, or really we could have noted this before we had the formula as well, is that the function f is always between 0 and 1. The values of the function f are between 0 and 1. So because it is a bounded function, the Laplace transform is going to be defined for every s bigger than 0. So we know the domain of the Laplace transform. Now let's go ahead and start calculating the Laplace transform now that we have this algebraic formula from equation 3. Again, I'm going to be using the notation from Boyce and Diprima. Use this calligraphy L applied to f to denote the Laplace transform. Then the next part of the equation is literally just the definition or the formula used to calculate the Laplace transform. I take my function, I multiply it by e to the negative st. So this is the Laplace transform at the value s. I integrate that with t going from 0 to infinity. So now instead of writing f of t, I'm going to plug in that algebraic formula that we got for f of t. Nothing too fancy happening here. And now, for the next step, that takes me to equation 5, I switch the order of the infinite sum and the infinite integral. Now, if you go on to take higher level math courses like real analysis, then you'll learn that you can't always do this. This is a pretty technical and detailed step on when you can and can't interchange integrals and summations, or infinite integrals and infinite summations. But this is part of a introductory differential equations course, so I'm not going to worry about those details for now. I'm just going to interchange the sum and the integral, and if you go on to take a real analysis course later on, then you can worry about those details. But just want to point out that there is something happening behind the scenes here. It's just beyond the scope of this course to discuss it in more detail. That being said, We go ahead and interchange the summation and the integral. And now I'm just going to calculate each of these individual integrals and then plug them back into the summation. But this is going to take a bit of work, so we're going to go on a little detour to calculate these integrals, and then we're going to come back to the summation later on. These integrals, I'm going to break them up into two pieces. So I'm going to first calculate the piece with uj. So uj t times t minus j times e to the minus st. I'm going to integrate that. And then I'm going to integrate the other piece, which is negative uj plus 1t times t minus j times e to the minus st. So let's go ahead and examine this first piece, which is going to be right here. Right. Yeah. So first piece, uj of t times t minus j times e to negative st. There is a formula in the textbook. It's a theorem 6.3.1 of the 10th edition of Boyce and Diprima that would let us calculate this fairly quickly. But I just want to do this one step by step, and then later on I'm just going to use that theorem. Because it's a nice theorem, but you don't have to use it, so I thought I would just show both ways, with and without the theorem. So to just do this directly, without the theorem, I want to do a change of variables. I want to replace the t with t minus j. So since I want that to be the case, I need this t up here, right? This t up in the e to the minus st in the integral. I want to turn that into a t minus j. So when I go ahead and make a t minus j up there, so let's say this t minus j, I have to introduce this term to keep it even. This e to the negative sj cancels out with e to the negative j. So e to the positive j. So that's why the left-hand side and the right-hand side are equal, is because I put in this term to cancel out that term. But the benefit of doing this is that I now have t minus j. So I can go ahead and do a shift. So technically, if I was doing u substitution, I would change variables to u. But because this is a basic u substitution, let's try that again. I decided to make some adjustments to the notes to make this explanation of the substitution more clear. So to go from equation 6 to 7, I'm going to make a u substitution, or really I'm using the variable tau, so a tau substitution if you want. I'm going to let tau equal t minus j, so that d tau is the same as dt. This t minus j turns into tau. This t minus j turns into tau. And then this t turns into tau plus j. So now the last two parts look good, right? Tau and e to the negative s tau, that's just what we normally see when we're working with Laplace transform or just functions in general. Don't have to deal with that pesky shift by j. But this term here still looks a little bit annoying. This uj plus 1 of tau plus j. But thankfully, it just goes away, right? Uj of tau plus j is always equal to 1 because tau starts at 0 and goes to infinity in this integral. And then that's why it just disappeared here on the next line. So there's two things that I'm going to explain to you here. First of all, let's look at this uj of tau plus j. And then the second thing I'm going to come to in a moment is the bounds of the integral. So uj of tau plus j. Here's our graph of uc. So in my integral, I started at tau equals 0 and went up to infinity. Now, when tau is 0, that's the very beginning, I add j to it, or in this case, c. Down there, I had uj, tau plus j. And since this picture has uc, I'm just going to say tau plus c. So 0 plus c, 0 plus the index of my step function, takes me all the way right up to here, where the step function is 1. And then as tau gets bigger, tau plus c also gets bigger, so the step function is just always going to be equal to 1, like I said it would, and then it just goes away. 1 times anything is just, it leaves the quantity unchanged. Now, the second detail I brushed over is that when I did this substitution of tau equals t minus j, technically the integral should start at negative j, right? Because here it starts at t equals 0. So if tau is 0 minus j, then this integral should start at negative j. Now, when tau is between negative j and 0, but strictly smaller than 0, and I then add j to it, tau plus j is going to be smaller than j. So when tau is between negative j and 0, tau plus j is between 0 here and j, or in this case c. So then the function value, the value of the step function is 0, and 0 times anything is 0, so that whole part of the integral is just 0 and goes away. So that's why I didn't actually shift the bounds. You could shift the bounds, and then that part of the integral is 0, so it goes away. Then, for the part that's left, the step function is just 1. So then the step function goes away, but the rest of the function, the tau times e to the minus s tau, stays. And then, once we get to this point, we realize that this integral is just the Laplace transform of tau, or if you want, the Laplace transform of t. So if we look that up from a table, or if we just memorize it because it's one of the basic Laplace transforms, then the Laplace transform of tau, evaluated at s, is 1 over s squared, and I multiply it by this e to the negative sj, so it becomes e to the negative sj over s squared. Now, the results of equations 6 to 8 also follow directly from theorem 6.3.1 of Boyce and Diprima, and we're going to use that for our next calculation. So in summary, what we've done is we've calculated the first part of this inner integral. It's come out to be e to the negative sj over s squared. Now we're going to move on to calculate the second part, the part with the u to the negative j plus 1 of t, which is right here. Now, this time I'm not going to do the previous calculations. I'm just going to use the theorem from the textbook. But before I do that, I need to have some additional preparation. So I have a j over here, but the index of my u is j plus 1, not j. So I need to turn this j into a j plus 1, and that's why I made the little adjustment here. Right, this negative 1, excuse me, there we go, negative 1 plus 1 is 0, so that all cancels out and turns out to be the same as what we had before. But the benefit is I now have a j plus 1 to work with. So I'll distribute both of these terms, the uj plus 1 of t and the e to negative st. I'll distribute them over the t minus j plus 1. and I'll distribute them over the plus 1, and then I'll split the integral to get these two separate integrals. Now, this first integral is going to be the Laplace transform of uj plus 1 of t times t minus j plus 1, right? Because I am taking this function, I'm multiplying it by e to the negative st, and then taking the integral. That's how I made this observation. It's just, I'm using the definition of Laplace transform, but I'm using it backwards. I'm starting from the formula of the Laplace transform, and then I'm going back to just writing Laplace transform of this function. Negative sign on the outside stays there, and I'm going to do the same thing for this other integral. I'm just going to identify this integral as being a formula for the Laplace transform of the step function uj plus 1 of t. And I'm going to be very explicit with my details. I don't need this times 1 here, but because I'm about to use the theorem from the textbook, I'm going to write this times 1 just to make it more obvious how I'm using the theorem. So this is really just the Laplace transform of uj plus 1 of t. And uj plus 1 of t is the same as uj plus 1 of t times 1. Now, before I use this theorem 6.3.1 that I've mentioned so many times, let's actually take a look at it. Here is theorem 6.3.1 from the 10th edition of Boyce and Diprima. So if we look at this line over here, right, this is the main part of the theorem that I'm using. It's part 5. So the Laplace transform of this step function uc of t times some function f evaluated at t minus c, so I'm shifting the argument of the function by c, that index of the step function, is going to be the same as e to the negative cs times the Laplace transform of the original function. So over here, I got rid of the shift in the function. It's now just f of t instead of f of t minus c. And I got rid of the step function uc of t. And then over here, they just went a step further, where previously they defined the Laplace transform of lowercase f to just be capital F, and then they just put in the capital F there. So really, I'm just focusing on the first two parts here. Now, if we go ahead and use that, the Laplace transform of this is just going to turn out to be the Laplace transform of t. So yeah, let's do this. I'll first highlight the t, and then there we go. And a little bit more there. So the Laplace transform of all of this is going to turn out to be e to the negative s times j plus 1, which is what we have here, times the Laplace transform of t, which is just 1 over s squared, and then the negative sign from the outside stays. And then similarly, I'm going to have that here. Let's see if I could do this part more effectively. There we go. The Laplace transform of uj plus 1 of t times 1 is going to be e to the negative s times j plus 1 times the Laplace transform of 1, which is 1 over s, and then the negative sign stays up front. And the interesting thing here is the function 1 This might be a little confusing because you can see over here I had the t minus j plus 1, and then it just went back to being t, right? The shift in the formula f of t minus c just turned into f of t. The shift went away. So if my function is f of t equals 1, which is what's happening here, right? This is f of t equals 1. No matter what t you put in, you get 1. Then whether I work with f of t minus c or f of t, it's the same function. I'm just going to get 1 all the time. So I am still getting rid of the shift, but it just so happens that when I get rid of the shift, the function 1 remains unchanged. So I just take the Laplace transform of 1 and get my 1 over s. And then I put the two of those together, and then that is the conclusion of these calculations, is that this is, there we go, the value of this integral, the second part. So now if we put together the results of both calculations, the dark gray and the light gray, then we get the value of this inside integral, which was our goal all of this time. So everything we did from equation 6 up to 12, we put those results together and we get the following, right? Let's just reiterate. This turns into, this time I'll include the negative sign. Turns into that, and that turns into that. So we calculated the integral, and now we're going to plug that integral back into this summation, right? So just to summarize, we had this summation. I'm going to plug this integral into it. That's the result of all of our previous hard work. And now we get to use another fancy trick in math. We get to use telescoping summations. And now you'll notice a jump in the video because I wanted to edit the PDF to add in some more details to show you the details of telescoping summations. So we were at this equation 15 where we had evaluated integrals, and we have now reduced the problem to evaluating this infinite summation. So the first thing we're going to do is we're going to, instead of taking an infinite summation of 3 terms, I'm going to split this up into 3 infinite summations of individual terms. So I'm gonna take this first piece and move that into one summation, and then I'm gonna take the second piece and put that in a different summation, and take the third piece and put that in a third summation. Now, technically, again, if you take real analysis, you'll see that it's not always obvious that you can do this. When you're adding a finite number of things, you can add them up in any order that you'd like, and that's never going to cause a problem. When you're adding an infinite number of things, you have to be careful as to whether or not you can add them up in any order that you'd like to. But the details of that, again, they go beyond the scope of this course, so just know that there is something that should be checked, but we're just not going to check it. And what's happening here is, in equation 15, I'm first adding up the yellow term to the orange term to the purple term, and then I'm taking an infinite sum of each of those results. In equation 16, I'm just changing the order in which things are happening. I'm first adding up all of the yellow terms, and then I'm adding up all of the orange terms, and then I'm adding up all of the pink terms, and then I'm adding those results together. So again, all that happened between equations 15 and 16 is that I added up the terms that we had, but in a different order. And now we can see that I'm leaving this pink term untouched for now. And I'm going to focus our attention on the yellow term, which is in between these yellow parentheses, and the orange term, which is in between these orange parentheses. So this is where the telescoping is about to happen. That first step I showed you was kind of just preparation to show my work. Now this is the real telescoping. This first term over here, I'm not going to be able to do anything with that. So that first term, I just simplify it, e to the negative s times 0 over s squared is just 1 over s squared, so I'll move that down. But now for all these other terms, we're going to obtain a lot of cancellation. So for example, we see that this term, positive e to the negative s times 1 all divided by s squared, cancels with negative e to the negative s times 1 all over s squared. And similarly, positive e to the negative s times 2 all over s squared cancels out with negative e to the negative s times 2 all over s squared. So we can see that each term from the yellow parentheses, from our first summation, cancels out with the term from the orange parentheses that's coming one before it, so to say, right? The second term in the yellow parentheses cancels out the first term in the orange. The third term in the yellow parentheses cancels out the second term in the orange. And the fourth term in the yellow parentheses, if I had written it, it would be the negative s times 3. That would cancel out with the third term in the orange parentheses. So other than the very first term, which I highlighted in pink from the yellow parentheses, every other term from the yellow and orange summations cancel each other out. And that's why it's like a big telescope and they all collide together down to that one term, the very first term. So that's how we get to equation 18. We go ahead and do all of those cancellations, keep that first term, the 1 over s squared. And then once again, that purple or dark pink summation, I still haven't changed it. I've just been keeping it there unchanged. But now that we've gotten rid of everything else, we can go ahead and focus our attention on this last summation as well. It turns out it's just a geometric series, so pretty easy to handle. I'm just going to do a little bit of preparation beforehand to make it obvious that it is a geometric series. So this negative sign, I'm going to take that outside of the summation. And this 1 over s, I'll take that outside of the summation as well. 1 over s, or if you want negative 1 over s, is independent of j, right? The j here in the summation. And that's why I can take it outside of the summation. It's kind of like how you could take a constant outside of an integral. That's what I'm doing here. Negative 1 over s is constant relative to j, which is what's changing in the summation. And that's why I can take the negative 1 over s outside of the summation. And after I do that, I'm going to go ahead and just change my indices. We can see that I had this little, let's go with that color. Instead of j plus 1, I'm switching it to j, right? So over here, I'm changing indices. When j is equal to 0 up here, j plus 1 is 1. And when j is 1, j plus 1 is 2. So we see that this sum is, the values of j plus 1 are 1, 2, 3, 4, so on. So that's why I made this change. Now it's just j instead of j plus 1, so it's a little bit simpler. And sure enough, I just started at 1 instead of 0, so it just goes 1, 2, 3, 4. And normally when you do this, you should use a different letter, right? Because this j is not the same as this j, so a little bit sloppy of me. to use the same variable, but it's not too big of a deal. Point being, it should now be clear to us after we make that change that we have a geometric series. So we go ahead and use the geometric series formula to write this series as e to the negative s over 1 minus e to the negative s. And that gives us the final answer to the problem. So I did a little bit of simplifying here. It's kind of optional. Whether you stop here or make the simplification that I did, either way is fine. We have calculated the Laplace transform of the periodic function that we were given in the very beginning. So that's all that I have for this problem. Hopefully you liked the video, and if you did, give that a like and subscribe.